So here's lesson 3 in our unit on the special theory of relativity. And we start today by saying that if Einstein's theory of special relativity is true, then we have to say that our notions of what relative motion is not important and can't exist anymore when we're measuring the speed of light. And the reason that that can't be true is because we can never go faster than the speed of light. It's an absolute quantity. In addition to that, we're going to have to do away with all of our common sense notion of time and space. We're used to looking at speeds and looking at displacements and accelerations where we can visualize and we can see the objects moving around. None of us has experienced what it's like to travel close to the speed of light. And so really some of the problems that this is that we don't have experience with these types of motions. And it's really wacky, some of the stuff that's going to come out of this. And there's two major effects that we're going to talk about, and then there's one famous paradox at the end that we're going to look at. And there's more and more to come. But those things that we're going to look at, the more in-depth consequences of special relativity, we're going to investigate at the end of the course, once we've learned more physics. So really, the first thing that we want to investigate is that moving clocks run slow. And this is known as time dilation. And it's one of the effects that we're going to discuss. It's one of the consequences of special relativity. And we're going to go through a thought experiment and a little bit of a derivation in the next couple of slides to get at the end result. The end result is really what's most important. The reason that we're going to go through the derivation is because it's important to appreciate where things have come from so that we're not just using formulas to try and plug and chug. Because if we do that, we're going to run into problems. We really have to understand the physics of where things come from. So on with the first thought experiment. Alphonse is in a boxcar traveling at a speed v. Okay, and he performs the following experiment. He sends a pulse of light from the floor up towards the ceiling. It hits a mirror and it's reflected back to the floor. So that's what he performs. That's the experiment. And he measures a couple of things, right? So here he is in his boxcar. The boxcar is traveling at a speed v. And the boxcar has a height of h. And he sends his pulse of light up, and then it hits the mirror and it comes back down. So let's use distance equals velocity times time. And let's say that, okay, well, the distance that laser light is going to travel is 2h. And the velocity, of course, that the laser travels at is the speed of light, which is c. And so we can say, all right, well, let's have an expression. Here's an expression right here for the time that Alphonse measures that it's going to take this light to go from the floor up to the ceiling and back. And all this has come from distance equals velocity times time. Okay? So now we have Beauregard, and she's an observer that she's standing outside of the boxcar. She's on the ground, and she watches the boxcar go by. But she notices something a little bit different from Alphonse. From Beauregard's point of view, the light travels up to the ceiling while the boxcar moves sideways. And she notices that the light travels farther than Alphonse does. So this is what she sees. Here she's on the ground, and so she sees this is an image of the boxcar at 3 different spots. So bing, bing, bing. Well, what does she see the light do? She sees the light leave the ground and move up to the mirror, and then reflect off the mirror and move back to the ground. So this is what she sees. And because the laws of physics have to obey, have to agree in all reference frames, if she notices that the light travels farther and the speed of light always travels at the same velocity, she has to measure a time that's greater than what he measures. So let's finish this off. Here's a diagram of the path of the light. And we're going to call the distance that light travels here r. We're just going to call it r. So it goes from this bottom corner and it travels a distance r up to the mirror, which is a height h above the ground, and then it travels back down. And the distance along the bottom of this triangle is just velocity times time as she measures it, because the train's moving at some velocity v. And so here we have a Pythagorean relationship that we can say. We can say, okay, well, then we can say that r is equal to vt over 2 squared plus h squared. And so we've used the Pythagorean theorem now, which should be fine. And we're going to go on to do a couple more little things so that we can derive an expression. Because what we want to do ultimately is relate the time that he measures to the time that she measures. Because after all, we're talking about time dilation. And so we have said if the laws of physics have to be the same in his point of view, in his reference frame, and in her reference frame, that's Einstein's first postulate, and light can never travel faster than the speed of light, it always travels at c in a vacuum, that's his second postulate, then A and B must measure a different time for the experiment. And so what we want to do now is we want to take what we've done in the first couple of pages, and now we want to set an expression that relates the time that he measures to the time that she measures. So here we have time as she sees it, which is equal to 2 times the distance r divided by c. All right? And we can then say, okay, well, we actually have an expression, though, for r. And that expression for r we got from the Pythagorean theorem. So here we go with a little bit more to the story. And we can now say that T naught is equal to 2h over c. So we want to get rid of the h because we have no interest in the height of the boxcar. But we have this expression, T naught is equal to 2h over c. That's what Alphonse measured inside the boxcar. And this is going to be where we can relate the time that she measures and the time that he measures. And so we can put these two things together and we can say, oh, well, here's an expression. We've got a couple of t's, and we've got a t naught, and we've got c and v. All right, no problem, this could work. Through a whole bunch of algebraic manipulation, and it's not difficult to do, and in fact, if you want an exercise, you can try and show that these two lines are the same, but through algebraic manipulation, we can show that this first line is equal to this second line. And if you're really, really eager, you can do even more algebra, and you can show that this final expression is in fact the exact same thing. So time measured by Beauregard, t, is given by this equation as it relates to t naught. And so here we find that t is relativistic time, and it's measured in a frame of reference where the beginning and the end of the experiment occur at two different points of space. T naught is proper time, and it's measured in a frame of reference where the beginning and the end of the experiment occur at the same point in space. And this is our expression for time dilation. So to take a look at what we mean, we're going to investigate an example. And so here in an example, we have the period of a pendulum is measured to be 3 seconds in the reference frame of the pendulum. Okay, so the pendulum swings to its one position and then swings back to its initial position, and it takes 3 seconds to do that. Of course, here it is in the reference frame of the pendulum. Of course, the ball at the end starts in one position and it ends in the same position. And that's, of course, what period is measured to be. What is the period then when measured by an observer traveling at a very, very high speed, 0.95 c, relative to the pendulum, excuse me. And the first thing you have to say is, hold on, in our little derivation, we said, oh, well, it was the observer that was stationary and the guy doing the experiment was moving. Here, this is a little bit different. Now we've said that, well, the pendulum is sitting still and the observer's moving. And of course, it isn't a problem because we're talking about relativity. So it doesn't matter if the pendulum's moving at 0.95 c or if the observer moves at 0.95 c. It's all relative. And that has to do with Einstein's second postulate. So fair enough. Now we can begin our problem, and we can say, okay, well then t naught, which is proper time, because of course the pendulum starts and stops at the same spot, that's 3 seconds. And the velocity of the observer in this case is 0.95 c. So let's put this into our equation for relativistic time. And we find, once we do the substitution, that we have this factor in the denominator, which is going to give us an answer of 9.6 seconds. Now, you'll notice here in the second fraction, where we have this denominator, this algebra, sometimes to work out on a calculator, if you're not really skilled with calculator work, it may take you a couple tries to kind of get used to this, because of course the C's cancel, and you got to remember bed mass, and you got to be really careful. I've done it in a couple of steps. For a novice, you may have to do it in a few more steps than I have, but basically what we see is that the period is measured to be 9.6 seconds long. So time for the pendulum, proper time is measured at 3 seconds. Here an observer moving very, very, very quickly is going to see time being longer, and this is an example of time dilation. So the next consequence of his special theory of relativity is length contraction, and that's that moving objects appear shorter. And it's another effect of the special theory of relativity. If time is relative, then using the relationship that we just developed for time being relative, we can show that length measurements are also relative. And so here's a second thought experiment. Clyde is traveling on a spaceship from Earth to Mars, moving at a speed v. So, of course, we know in real life that Earth and Mars are always moving relative to each other. We're going to assume for this thought experiment that Earth and Mars are fixed in space and are at rest relative to each other. And they are located a distance of L0 apart. So here's a little diagram of our situation. We've got Earth, we've got Mars, and we've got a distance of L0 that separates them. Delilah, she's an observer on Earth. And so using distance equals velocity times time, she says that the time taken for this trip is t equals L0 over v. Proper length, then, is the length that's measured in a reference frame in which the observed object is at rest. So the observer is at rest. This is the length, that Delilah is measuring, because she's at rest and she sees, okay, there's this distance between the two planets. For Clyde, he's moving. So he says that proper time, that's the time that's measured on his spaceship. He says that the time's less because time dilates. And Clyde sees himself at rest. He sees Mars approaching. He sees Earth receding. And so putting these two things together, we can calculate the relativistic length of Clyde's trip, according to him. We can say, okay, well, we've got our formula for time dilation. And we say, okay, well, Clyde's traveling at this speed v, no problem. And so we can say, fair enough. Here's a distance. Let's multiply both sides by the speed that Clyde's traveling. So Vt is equal to Vt naught over our Lorentz factor. And we can say, fair enough. Vt is equal to 1 minus v squared over c squared, which equals Vt naught. And this is what's defined as relativistic length. We can say the length from Clyde's point of view is equal to proper length times the Lorentz factor. So this, again, needs a little bit of investigation through an example. But first, we really do need to point out, because this is a little bit wacky, velocity times relativistic time is equal to proper length. And over here, we've got velocity times proper time is equal to relativistic length. So we've got these two different things. We've got relativistic time giving us proper length, and we've got proper time giving us relativistic length. And that's an important point of view to get through, is that, okay, well, time as measured by a moving observer is proper time. But because he's moving, that's relativistic length. And time measured by a stationary observer is relativistic time, but is proper length. And so we have these two things that are back and forth, and this is one little factor that can kind of mess us up, and it's one thing that you have to be wary of. So let's take a look at an example. A spaceship is measured to be 120 meters long while at rest relative to an observer. If the spaceship flies by the observer at 0.99 c, what length does the observer measure? So we've got our proper length, right? Because proper length is the time, or sorry, the length that is relative to an observer at rest. And we've got the speed, so we can put this into our formula. We can say, okay, well, here it is. And we have this other factor then underneath the square root sign that, again, you may need to take a little bit of time to actually get your calculator to give you the right thing. But what we get is a factor of 0.1411. And when multiplied by 120, we find that, oh, well, the relativistic length, the length that the observer measures, is 17 meters. We can say, oh, that's quite a bit shorter. And that's because moving objects appear shorter. One of the most famous paradoxes in special relativity is the twin paradox. And a paradox in general is a situation where people can reach contradictory conclusions using valid deductions, right, from premises that are acceptable to everyone. And so here's the twin paradox. A set of twins named Eunice and Francisco reach an age of 20 years old. Eunice, who's more adventurous, sets out an epic journey to the planet X. And this planet X is located 20 light years from Earth. Her spaceship is capable of traveling at a very fast speed, 0.95 c, relative to the inertial frame of her brother back home. However, after reaching the planet X, Eunice becomes homesick and immediately returns to the Earth at the same speed of 0.95 c. Upon her return, Eunice is shocked to discover that Francisco has aged 42 years and is now 60 years old. Eunice, on the other hand, has only aged 13 years. So here's two twins, and because of time dilation and length contraction, they age at different rates because their clocks and the distances that they travel are different to both of them because one of them is going very, very fast. The paradox we'll talk about later, but first we better verify that all these things make sense, that the numbers actually add up. And so here's our final example of the unit. Let's verify the ages of the twins in the situation described above. So we're going to start with our givens. Proper length, which is the distance between here and the planet X, is 20 light years. And for a light year, we just write CA, right? So 20 times the speed of light, and it's that many years. So 20 light years. The velocity at which Eunice is traveling is 0.95 c. So let's take a look at Francisco first, because he's sitting on Earth, and he's aging the most. And we have, okay, what time, how long, according to him, is it going to take her to get to the planet X and come back? Well, it's going to be 2 times the length, or the distance that she travels, divided by the speed that she travels at. So all this is distance equals velocity times time again. And if we put these numbers in, we get 2 times 20 light years divided by 0.95 c. And when we do this calculation, it equals 42 years. So for him, he's okay. He's aged 42 years. Let's take a look at Eunice, though. She's traveling. And so we have to use proper time to describe her trip. And we have to use relativistic length to describe her trip because that's her reference frame. She's traveling, and she's traveling in a different frame. So for her, we know that relativistic length, we need to be able to find an expression for that. Well, we happen to have an expression, and it's this expression right here. So let's actually solve first. Instead of solving for how many years she ages, let's solve for how far her trip happens to be, according to her. And we plug in our numbers, 20 light years, multiplied by this factor. And what it gives us is 6.245 light years. So she would actually argue that she didn't travel 20 light years because she's traveling so fast. She actually only went 6.245 light years. And so the amount that she ages then is 2 times 6.245 divided by her speed, which is 0.95 c. And of course we get 13 years, which is as expected. So the numbers jive, everything's fine, and because we kind of held to the exact definitions of what everything was, the ages agree with the paradox. However, we said that we'd come to the paradox at the end, and this is the paradox. Which twin was actually the traveler? Because from Francisco's frame of reference, he stayed at home and his sister traveled. But from her frame of reference, she was at rest and her brother traveled. When we're talking about these frames of reference, we said it doesn't matter who's moving and who isn't. So we've just proven that he was the one that stayed at home and she was the one that did the traveling, but it doesn't have to be like that. So the question then becomes, what is the problem with the twin paradox? And how can we be sure that it was him that did the traveling and not her? And of course, the answer to the question is that as she accelerates away from Earth, gets to the planet X, decelerates and turns around, and then comes home, she's not traveling in an inertial frame of reference, because we've said that inertial frames of reference have no acceleration. And so because she must have accelerated and she must have decelerated times 2, she's traveling in a non-inertial reference frame. And of course the twin paradox is not really a paradox. It violates one of Newton's premises that all of this stuff that he derived was only based on the fact that it could only be used for inertial reference frames. And of course we violated that because she went and she turned around. So of course it was her that was moving, and we couldn't say that it went the other way around. And of course that's the problem with the twin paradox. So it actually isn't a paradox at all. And that, ladies and gentlemen, is lesson number 3.